Good morning, everybody. We shall continue with our section on triple integrals. So, section 9.15 triple integrals. In today's lecture, we shall be discussing in detail about the cylindrical and spherical coordinates, which we had done in the last section, and we'll just see the geometric representation of these two type of coordinates, and we shall do a few examples also. That is how we can just like we had converted the normal integration by dx dy with respect to x and y to the polar dr d theta, and similarly we can do the same in case of cylindrical and spherical coordinates also. So first let's just look into the geometric explanation of the cylindrical coordinates concept. So as you can see in figure 9.15.6, if we have to represent a point in the plane xyz, this is our xyz plane and P is a point, it is represented by the coordinate x, y and z. We can use the polar form r and theta also to represent this. That is what we had done for cylindrical coordinates. So for that, what is done is we are considering, we'll choose a point r theta in the xy plane corresponding to the z component of the point xyz. Okay, so we get r, theta and z. So this can actually be formed by considering z as a constant plane and theta also as a constant plane. So we will get a cylinder with the cylinder r equal to constant. So when there is this cylinder, r is equal to constant and the intersection of theta equal to constant and z equal to constant. Okay, all these three together will give us the point P. So here we are considering the cylinder, that's why the name cylindrical coordinates. So this is how the concept of cylindrical coordinates came, and we have done examples for conversion of cylindrical to rectangular, rectangular to cylindrical and all. Now next we shall be dealing with an example to solve the triple integral with the help of cylindrical coordinates. Now we shall see an example how to solve the triple integral with the help of cylindrical coordinates. So we had seen that we usually will evaluate the triple integral by using double integral over this integral, right? We had seen in the first lecture of section 9.15. so here this double integral over r can be replaced by integral variation of theta and integral variation of r into integral of f1 to f2 f of r theta z into dz into dA. We know when we convert into polar it will become r into dr into d theta. So that's what it is showing, r into dr into d theta. So that's how we shall use the cylindrical coordinate system to solve the triple integral. So we shall discuss example 5. The example is as follows. A solid in the first octant has a shape. Determine the graph of the cone z is equal to root of x square plus y square and the planes z equal to 1, x equal to 0, y equal to 0. So you can see figure 9.15.9. We have the shape of a cone, okay, and we have to consider only the first octant, that is what is asked, and we have the plane z equal to 1 and x equal to 0, y equal to 0. Now we are asked to find the center of mass if the density is given by rho of r theta z is equal to r. So in this example itself there is a clue given to us, that is the density is depending upon r and theta, and also when we have the function in terms of x square y square it is easy to solve them in terms of polar coordinates. So what we'll do, we'll convert it into polar coordinates. So we have to find the center of mass, that is we need to determine small m, then mxy, mxz, myx, myz and so on. So let's determine capital M first. So M is equal to nothing but the formula is triple integral over d r into dv, right? Now dv will be replaced by dz, dx, dy, dz, but dx and dy will be replaced by r, dr, d theta. Okay, so here first we shall integrate z. Here z actually varies from its given to us root of x square plus y square. So x square plus y square is equal to r square. So root of r square is r. So z varies from r to 1 Then in the figure you can see the projection of this region D. So this is our figure. So here small r varies from 0 to 1 and theta varies from 0 to pi by 2. So once we know the figure and the limits are clear, the problem will be easy to solve. So m will be nothing but integral over 0 to pi by 2, integral 0 to 1, integral r to 1. R to 1 is a variation of z, 0 to 1 is a variation of r, and 0 to pi by 2 is a variation of theta. Now we can solve this. So this will be nothing but r square into z varying from r to 1, that is r square minus r cube into dr d theta. So solving this, we will get the value to be pi by 24. And next we shall determine what is mxy. So mxy will be triple integral over d z r dv. So here the limits are the same. Again you can substitute dv to be r into dz into dr into dv. Solving, you can just verify it. The integration is simple, there's no much complication in it. Mxy turns out to be pi by 30. Now while determining mxz and myz, what we do is, it is actually mxz would be y into r into dv. So here we replace y by r sine theta. So we get r square sine theta dv. So we have mxz is equal to integral 0 to pi by 2, integral 0 to 1, integral r to 1, r cube into sine theta dz dr d theta. So we shall solve it, and the value comes out to be 1 by 20. Similarly myz is also equal to 1 by 20. So we can find the value of the center of mass. So the center of mass will have the coordinates x bar, y bar and z bar. X bar is myz by small m, which is 1 by 20 divided by pi by 24. Y bar is mxz by small m, which is 1 by 20 divided by pi by 24. And z bar is mxy by m, which is equal to pi by 30 divided by pi by 24. So that's how we can use the cylindrical coordinates to evaluate the triple integral. So next we have the spherical coordinate system. We consider point P in the xyz plane given by x, y, z, or this can also be represented by the spherical coordinate, which is the order triple rho, phi and theta. Now rho is the distance from origin to the point P. Okay, phi is the angle made by z-axis up to this ray OP. Okay, this is the ray OP, and phi is the angle between the positive z-axis and this ray OP. Next, theta is actually project this line, this ray OP to the xy plane, and we get the ray OQ. Theta is the angle between x-axis and this ray. Okay, so this is obtained by considering the cone and a sphere. Okay, sphere, rho is the sphere, cone is phi, and theta is a constant. So when they intersect, we get this particular point P. So this is how we can interpret the spherical coordinate system. So we shall also see an example. We have done examples for conversion of spherical to rectangular and cylindrical. Now we shall see how we can convert the corresponding, or we can evaluate the triple integral with the help of spherical coordinates. So in this case dv will be nothing but rho square sine phi d phi d rho d phi d theta. Okay, earlier when we had converted d into r and theta, we had dA was replaced by dz remains as it is, dA was replaced by r dr d theta. Here the volume dv will be replaced by rho square sine phi d phi d rho d phi and d theta. Okay, so let's see an example. We are asked to find the moment of inertia about the z-axis, that is we have to determine Iz, right? And of the solid between the spheres, we are given two spheres, x square plus y square plus z square is equal to a square, and x square plus y square plus z square is equal to b square. So the density is given to be k. So Iz by definition it is triple integral over d x square plus y square into k into dv. Now what we do is we replace the value of x square plus y square with the help of spherical coordinate we'll have x square plus y square is nothing but rho square sine square phi. Okay, and now we know what is rho square x square plus y square in terms of spherical coordinate will be rho square sine square phi. We know what is dv is rho square sine phi dou rho d rho d phi and d theta. Now we just have to determine the limits. So here clearly the spheres are x square plus y square plus z square is equal to a square, and x square plus y square plus z square is equal to b square. So here rho equal to a and rho equal to b will be the spheres. They are the spheres. Now so we have the variation of rho, that is a to b, and we have phi. Phi is the angle made with the positive axis, so it varies from 0 to pi. You can see it in figure 9.15.2. Phi varies from 0 to pi and theta varies from 0 to 2 pi. And we have to evaluate this. It is simple. This is equal to, okay, there is just we have to make the substitution of sine cube phi. Sine cube phi can be treated as 1 minus cos square phi into sine phi. Okay, we have done these type of integration earlier also. So that's it. I hope this example is clear. So we have seen how we can use the corresponding spherical coordinate to determine the triple integral. So, and we have also discussed about the conversion, or how to solve the triple integral with the help of cylindrical coordinates as well in this lecture. So we shall do further examples to make this concept clear. So with this we shall wind up today's session. Thank you. Stay home, stay safe.